Welcome to the deep dive. Today we're tackling a concept that really it separates a clever language model from what you might call a truly autonomous machine. And that concept is memory.
That's right. You send over a fascinating set of sources that really unpack these complex, multi-layered memory systems.
They're the systems that turn large language models, LLMs, into what we're now calling capable agents.
Exactly. And our mission today is to give you the blueprint, really, for the cognitive architecture of advanced AI. We have to move beyond this simple idea of just having a long context window.
Which was the big thing for a while.
It was. But now we need to explore the specialized structures, the mechanisms, the life cycles these agents use to persist, to learn, and to evolve over time.
Okay, so let's unpack this. We're moving from what were essentially, I don't know, stateless calculators to something more like digital beings that actually have a history.
That shift is staggering, you're right. And understanding the memory architecture is really the only way to grasp that evolution.
So here's the plan. We'll start by establishing a clear, unified definition of what an LLM agent actually is. Because, well, that's been a bit confused historically.
A bit, yes.
Then we'll break down the three fundamental forms that memory can take. We're going to token, parametric, and latent.
And finally, and this is the crucial part, we'll analyze the dynamic processes, how memory is created, how it's maintained, and of course, how it's retrieved.
That last point about dynamics, you said it's crucial. Why is that?
Because memory isn't a passive bucket you just drop information into. It's an active cyclical process. It's formation, evolution, and retrieval, and it's running constantly.
So if you miss that loop...
If you miss that dynamic loop, you miss the essence of agency itself.
All right. Let's start with that definition of an agent then. Because just a couple of years ago, the line was, it was incredibly blurry.
It was a very confusing time in the field. I'm talking specifically about the period between, say, 2023 and 2024. The source material really highlights this significant historical ambiguity.
What did that ambiguity look like in practice?
Well, you'd have research papers where prompting an LLM to just call an external calculator API was enough to get the system labeled as an agent.
That seems like a pretty low bar for autonomy.
It's an incredibly low bar. It represents a system that's just performing a single simple action based on explicit human direction. It's reactive, not proactive.
So if the definition was that loose, what were those early models missing? What was the key ingredient?
Persistence and self-determination. They were just reactive components. They weren't proactive agents.
And on the other end of the spectrum?
Well, you had other, arguably more sophisticated systems at the time that acquired these rich capabilities, explicit planning, recursive self-improvement, tool mastery, reflective reasoning. Only then did they earn the title.
So there was no consistency?
None. No stable, coherent set of expectations for what the word agent even meant.
But the field has matured so quickly since then. We now have a much more unified and structured understanding. So what defines the modern LLM agent stack now?
The recently unified definition is, thankfully, very clear. An LLM-based agent is the core LLM plus a crucial set of, let's call them non-negotiable capabilities.
Okay, what are they?
We're looking for systems that can demonstrate reasoning, planning, memory, tool use, self-improvement, multi-turn interaction, and perception.
So when you see that whole stack together...
When you see that comprehensive stack, you realize we're talking about autonomous, goal-directed behavior that operates across extended time horizons. It's not just about generating a single text completion anymore.
The agent is a system designed for goal execution then. And memory is what maintains the state of that execution.
Precisely. And that goal-directed behavior, it manifests through concrete actions. These observable actions are the raw material, the stuff that gets processed and turned into memory.
And the sources identify 5 core action types that sort of define the agent's interaction with its world.
Exactly. These are the things we can actually see when an agent is running its course.
What's the first one?
First, you have natural language generation. Now, this is the one we're all familiar with, but it's expanded here. It's not just about responding to a user.
It's internal, too.
It's internal. It includes artifacts like intermediate reasoning steps, explanations the agent generates for itself, or structured instructions for its own internal components. These are, in a way, the verbalized thoughts of the agent.
The second one is probably what most people think of when they hear agent.
Tool invocation actions. Yes. This is often the first really visible sign of agency. It's the system deciding on its own that it needs outside help,
Like calling an API or using a search engine.
or executing code in a sandbox, or querying a specialized database. This is how the agent gets around the LLM's static knowledge boundaries.
Okay, but the decision to use a tool, that requires some kind of internal, explicit process, doesn't it? The agent has to stop and think about what to do next.
It does, and that brings us to the third type, planning actions. These are explicit outputs that formalize the agent's thought process.
So it's not just thinking, it's writing down the plan.
Exactly. It might manifest as a detailed task decomposition, or a specific execution plan, or a clear outline of subgoals. These planning actions are themselves informational artifacts that the memory system has to capture to maintain coherence.
And what about interacting with the world? Not just a digital one, but a physical one, or at least a simulated one.
That's the fourth type, environment control actions. This signifies direct manipulation of the external world. In an embodied setting, this could be navigation or moving virtual objects.
Or in a software context?
In software engineering, it could mean editing a code repository or pulling data from a local file. At its simplest, it means the agent reaches out and actually changes its perceived reality.
And finally, you need something to hold multi-agent systems together.
Right, and that is communication actions. This is absolutely critical for collaboration or negotiation with other agents. It's usually done through structured, machine-readable messages.
So that communication log becomes a shared memory for all the agents involved.
It becomes a crucial part of what we'll later call environment factual memory.
Yes. Okay, so we have the agent, and we have its actions. Now let's clarify a really core distinction you made earlier. Agent memory versus LLM internal memory. This seems vital.
It is the most important conceptual hurdle to get over. When we talk about agent memory in this discussion, I want you to imagine it as the agent's persistent notebook, or maybe its hard drive.
Okay, so it's external.
It's the external, durable knowledge base that the agent uses across multiple decision steps. It could span days, weeks, or even entirely separate tasks. It's where the accrued experience and long-term history are stored.
And LLM internal memory, then, is more like a scratch pad.
A perfect analogy. LLM internal memory is about the intrinsic model dynamics that manage the current input sequence. This is things like managing the transformer's key value cache, the KV cache.
Which is just the activation history of tokens in the current processing step.
Exactly. It's transient. It's crucial for understanding the immediate input, but it usually gets flushed or overwritten once that forward pass is complete. So we're focusing on the persistent external knowledge that defines the agent's history.
And this is where it gets really interesting, because we're moving from just static storage to dynamic function. You said memory isn't static. It follows a dynamic three-step cycle.
A continuous feedback loop. These three operators, formation, evolution, and retrieval, define the entire journey of information from raw data to usable knowledge.
Let's start with the first one, memory formation.
So, at any given time step, the agent produces what the sources call informational artifacts. These are the raw outputs, tool outputs, reasoning traces, environmental feedback.
The raw data stream.
The raw data stream. The formation operator then selectively transforms these artifacts into memory candidates. And critically, it doesn't store the raw action verbatim.
It summarizes.
It performs a lossy compression, and it's driven by an estimation of potential future utility. It's asking what part of this is going to be useful later and writing down an abstract summary of that.
So, if the agent runs a complex piece of code, it doesn't store 50 lines of Python output. It stores the one-line conclusion. Tool successfully retrieved the user profile.
That's a perfect example. And once those candidates are formed, they have to be integrated.
Which is the job of memory evolution.
Right. This operator integrates the formed memory candidates into the existing memory base. But evolution is not a simple append operation. It's not just adding to a list.
What is it doing then?
It's a complex, multifaceted process that ensures lifelong learning and consistency. It includes consolidating redundant entries, resolving conflicts with older or contradictory information, and discarding information that's judged to be low utility.
This evolution step feels like what separates a simple RAG system, which just adds tokens to a database, from a true cognitive architecture.
It's exactly that. It makes the knowledge base dynamic and self-optimizing. And of course, the whole point of this cycle is to actually use the information.
Which brings us to the third step, memory retrieval.
Precisely. When the agent is selecting an action, it needs context. It retrieves a context-dependent memory signal, let's call it NUI type. This retrieved information then serves as a crucial input to the agent's policy, guiding its next decision.
So that brings us to this idea of agent memory coupling. The sources have this policy equation, which looks complicated, but it basically says the agent's action is a function of what it sees now, its static knowledge, and this retrieved memory.
It does, and what it illustrates is the architecture's flexibility. The key thing to notice is that the memory retrieval step is optional.
Optional.
Yes, if the agent determines autonomously that retrieval isn't necessary for the current step, that memory signal is treated as a null input. It decides not to consult its notes, so to speak.
That's a powerful insight. It means the agent is actually in control of its own memory use.
It is, and it tells us that agent memory systems aren't all the same. They range from passive buffers, where the agent always retrieves context, all the way to actively evolving knowledge bases, where the agent itself decides when and if to access its own history.
That self-regulated retrieval is the real difference between an autonomous agent and a traditional RA system.
Exactly. RA is usually prompted by a user. Agent memory is invoked and curated by the agent itself.
Okay, so if we connect this to the bigger picture, once memory has been formed and evolved, we need to know where it's actually stored, structurally.
Right. And memory systems and agents fall into three really distinct structural categories. They are either explicit and readable, which is token level,
Implicitly woven into the model's own knowledge, which is parametric.
or hidden away in the computational flow, which is latent. Understanding this structural framework is absolutely critical for analyzing the pros and cons of any agent design.
Let's start with token-level memory. This feels like the most intuitive one for anyone familiar with databases or RE. It's the physical external record.
That's right. Token-level memory is information organized as explicit, discrete units. And token here is a bit of a metaphor. It could be text snippets, vector embeddings linked to text, even visual tokens or audio frames.
And the key is that they're external.
They're external, accessible, editable, and easy to interpret. This makes them transparent, easy to audit, simple to revise, and naturally suited for retrieval, routing, and handling conflicts in the data.
But how you organize these tokens, the topology, that dictates how efficient they are for search and reasoning. Let's look at the subtypes, starting with the simplest one, flat memory.
Flat memory, or you could call it 1D memory, is conceptually the easiest. It has no explicit internal topology or structure. Just think of it as a vast list, a sequence, or a simple bag of units.
So the relationships between memories aren't encoded in the structure itself.
No, they only exist through semantic similarity. The main attraction is its scalability and operational simplicity. You can append or prune memories with very little cost. Systems like MemGPC and Memory Bank rely on this for tracking interaction histories.
But that simplicity must come at a cost.
A huge structural cost. Redundancy and noise build up very easily because there's no structural way to enforce uniqueness. And more critically, the lack of relational organization really limits compositional reasoning.
Can you give an example of that?
Sure. The model can retrieve 10 separate facts about two people, say John and Sarah. But without an explicit link in the structure that says John is Sarah's spouse, the agent has to spend valuable tokens and computation reasoning out that relationship every single time. The agent's coherence relies entirely on the quality of that one retrieval query.
So to fix that limitation, you have to introduce structure. And that brings us to planar memory, or 2D memory.
Yes, this is an explicit single-layer organization. It often takes the form of graphs, trees, or tables. The structure is explicit, but it doesn't have multiple levels of abstraction. Graph RG systems are the most common example.
What's the advantage of encoding those links between memories?
It allows the memories to leverage what the sources call collective synergies. By establishing explicit links, you support structured lookups and relational traversal. It's great for organizing specific facts and relationships, like knowing definitively that John is married to Sarah.
But the structure is monolithic. What does that mean in this context?
It means all the knowledge is consolidated into one layer, one massive graph or table. And that really hinders scaling as complexity grows. The construction and maintenance costs are high, and it can become too complex for a wide diversity of tasks.
Which naturally leads to the most complex structure, hierarchical memory, or 3D memory.
This is the architectural attempt to solve the scaling problem of planar memory. Hierarchical memory is structured across multiple layers with interlayer links. A great example is something called hierarchical aggregate tree, or HAT.
So you have layers of abstraction.
Exactly. You might have raw tokens at the base, summarized chunks in the middle, and top-level conclusions at the peak.
And the utility of that stratification.
It supports course-defined retrieval. Instead of querying millions of raw tokens, the agent can query the high-level summary first to get its bearings, and only then drill down to the granular details if needed. It massively improves search efficiency.
So to sum up token-level memory, its great strength is transparency and auditability.
Precisely. It's best for high-frequency updates, long-term agents needing stable knowledge, and high-stakes domains like legal or finance where you need a verifiable, traceable decision log.
Now we move inside the LLM itself to parametric memory. This isn't in a vector database. It's in the statistical knowledge encoded within the machine's actual brain.
Correct. Parametric memory is information stored directly within the model's parameter space, the weights and biases. It's accessed implicitly during computation, not through an explicit search. This makes it intrinsically suited for, say, broad pattern induction or consistent personality maintenance.
The sources split this into internal and external implementations. Let's start with internal parametric memory.
This is the foundational knowledge that's baked directly into the model's core weights during pre-training. The advantage is simplicity. There's no external storage, no retrieval latency. It's why a large model can already code or reason right out of the box.
Well, the drawback is the classic machine learning problem, the stability versus plasticity dilemma.
That is its Achilles heel. It's incredibly difficult and costly to update. And when you do update it, it is highly prone to catastrophic interference.
Let's unpack that term. What does catastrophic interference look like in practice for an agent?
Imagine an agent is an expert in both historical facts and basic algebra. You try to update its internal knowledge with the latest information about a historical figure. That small update can inadvertently overwrite the parameters responsible for recognizing fundamental math rules.
So the next day, the agent might forget how to add.
Or misremember Python syntax. It forgets old generalized knowledge when new, specific knowledge is injected. It's fantastic for storing foundational, static expertise, but terrible for tracking rapidly changing information.
Which seems to necessitate a compromise, which is external parametric memory.
This is the modular approach. Knowledge is stored in auxiliary parameter sets, things like adapters or LoRa modules, that are attached to a frozen base model.
So you gain plasticity without losing the stability of the core model.
It's the best compromise we have right now. You can swap out a LoRa module with old knowledge for a new one without altering the base model's core weights, so you avoid that catastrophic interference.
But the memory's influence is less direct, I assume.
It is indirect. The external parameters have to influence the core model's computation pathway, so their effect is mediated and sometimes weaker than directly encoded knowledge.
So parametric memory shines when the task demands structural insight and consistent behavior.
Precisely. Ideal scenarios are things like sophisticated role-playing, where a consistent persona is essential, or tasks that demand structural insight, like complex math, where the rules need to be fluidly and intrinsically applied, not just looked up in a file.
Their third structural form is latent memory. This is the memory carried implicitly in the model's internal representations, the hidden states, the KV cache. It sits somewhere between explicit tokens and fixed parameters.
Latent memory is the choice when performance, privacy, and scalability are your main drivers. Because it's machine native, its low readability gives you intrinsic privacy protection.
And it's fast.
Exceptionally low inference latency because it's embedded within the inference flow. It also has a high expressive capacity, preserving those fine-grained contextual signals that are so crucial for complex tasks like multimodal alignment.
The sources say the origin of latent memory falls into three pathways: generate, reuse, and transform. Let's start with generate.
Generate involves synthesizing new latent representations using auxiliary modules. A system called COMIM, for example, compresses continuous multimodal knowledge-like video and text streams into fixed-size plug-and-play embeddings.
And you can insert those into the prompt without a huge token count.
Exactly. The next path, reuse, is about leveraging the model's own immediate processing dynamics.
So using the KV cache directly.
Yes, directly leveraging the key value cache. If you externalize and maintain this raw cache, you preserve the full fidelity of the model's activations for context. It's conceptually simple.
But it must be incredibly expensive computationally.
It is. The raw caches grow very rapidly and can dominate your GPU memory. A simple 30,000 token sequence can require gigabytes of cache space.
Which is why the third type, transform, is so central to optimizing large models. It's all about aggressively modifying, compressing, or restructuring those latent states.
Transform-type methods treat the KV caches as malleable memory units and reshape them. This is where engineers innovate to manage context length without crippling performance. The goal is maximum information density with minimal storage cost.
Can you give a concrete example of a transformation mechanism?
A major focus is compressing the KV cache by keeping only the most influential tokens. Scissorhands is a great example. It doesn't just prune the oldest tokens, it dynamically estimates the importance of each token based on its previous attention scores.
So it's intelligent, importance-driven compression.
It is. Another strategy is H2O, or heavy hitter retention. It keeps the most recent tokens, because they're almost always vital, and simultaneously keeps heavy hitter tokens, the ones that had consistently high attention scores across the whole sequence, representing key concepts.
So these transformation techniques produce incredibly compact, information-dense memory.
But at the cost of fidelity and system complexity. That's the core trade-off. Compression introduces the risk of information loss.
Which makes latent memory ideal for resource-constrained environments.
Absolutely. Think multimodal architectures, on-device deployment at the edge, or privacy-sensitive applications where you don't want human-readable plaintext logs.
Okay, so now that we know what memory looks like structurally, token, parametric, latent, we can shift our focus to the function. Why do agents need memory in the first place?
This marks that paradigm shift from stateless components to adaptive, persistent decision makers. We categorize memory functionally into three main types: factual, experiential, and working memory.
This shift helps us understand the purpose the memory serves. Let's start with factual memory. This sounds like the agent's explicit historical knowledge.
It is the cornerstone. Its core purpose is to store and retrieve explicit declarative facts about past events, users, and the external environment. It's analogous to human declarative memory knowledge you can consciously recall.
And the sources split this into user factual memory and environment factual memory. Let's start with the user side. Why is this so critical?
User factual memory persists verifiable facts about a specific user preferences, routines, identity across sessions. Its primary function is preventing the classic failure modes of stateless interaction.
Like the agent asking for your name every single time.
That's a failure of factual memory, exactly. It's called corference drift. By storing and retrieving this explicit profile, the agent minimizes repeated questions and avoids contradictory responses. It achieves true personalization.
How do agents maintain that user coherence efficiently without storing every single conversation?
They rely on heuristic selection and semantic abstraction. Instead of retaining all the raw logs, systems rank entries by relevance or recency. And high-value interaction history is periodically condensed into higher-level summaries to maintain dialogue coherence.
Factual memory also supports goal consistency over long spans of time.
Yes. For a long horizon goal, like planning a week-long trip, the agent has to dynamically track the task state. It retains confirmed information while highlighting what's still unresolved. This helps the agent maintain focus and minimize intent drift across multiple sessions.
Beyond the user, agents need to remember their surroundings. That's environment factual memory.
This stores explicit facts about the external world or shared agent spaces. In systems like MetaGPT, shared message pools or hierarchical memory graphs serve as central workspaces. This provides knowledge persistence.
So it's like a common database, but used dynamically by multiple intelligences.
Precisely. It drastically reduces communication overhead because agents don't have to keep rebroadcasting results. It acts as a central repository for shared plans and constraints.
This seems incredibly relevant for social simulations, too.
It is the absolute foundation of social coherence. In platforms like Stanford's generative agents, the global environment and public interaction logs serve as a shared memory. When one agent discovers something new, that fact gets written to the public log.
So another agent can then find it and act on it.
Exactly. The information diffuses naturally throughout the simulated population, which supports coherent, history-aware social dynamics at scale.
Okay, so moving from declarative knowledge of what happened, which is factual, to procedural knowledge of how to act. That's experiential memory. This is where the agent learns skills.
Experiential memory is all about the dynamic accumulation of knowledge focused on action. It's the agent learning from its own execution, history observations, chains of thought, environmental feedback.
And the sources break this down into three types of increasing abstraction: case-based, strategy-based, and skill-based. Let's start with case-based memory. This sounds like storing the raw replay footage.
That's a perfect analogy. It stores raw trajectories, the specific observations, actions taken, and the results. Its strength is high informational fidelity. It provides verifiable, concrete evidence.
But the trade-off must be efficiency.
Huge efficiency challenges. It means high context window consumption and a massive headache trying to find the one relevant case out of a billion.
So if case-based memory is what happened, strategy-based memory is focused on extracting the reusable blueprint from that.
Exactly. This extracts transferable knowledge by generalizing patterns. It includes reusable reasoning patterns, abstract insights, efficient task decompositions. It's the agent reflecting on its successes and failures and formulating high-level principles.
How does that abstraction help?
It acts as a high-level scaffold to guide subsequent reasoning. A system might induce a reusable workflow, a template for debugging a Python script, and use that abstract guide to direct its planning process.
But those strategies are still just guidelines, right? They're not executable code.
That's the limitation. They are templates, not tools, which necessitates the third type, which connects insight to execution, skill-based memory.
This is the active execution substrate, the callable capabilities.
It is the executable component. It stores callable tools, code snippets, APIs, procedural scripts. It bridges abstract planning and environmental interaction.
The classic example is Voyager in Minecraft. How does it use skill memory?
Voyager constantly refines its skill library. When the agent successfully crafts a diamond pickaxe, the trajectory is analyzed, and the successful code is consolidated into a reusable skill. The next time it needs a pickaxe, it doesn't need slow, step-by-step reasoning. It just invokes the craft diamond pickaxe skill.
So complex systems have this dynamic transition. Raw experience becomes an abstract strategy, and a successful strategy becomes an efficient skill.
It's an automated process of proceduralization. It's the shift from slow retrieval to rapid, reliable execution. That transition is what defines advanced agency.
Our third functional category is working memory, the immediate, active workspace for inference. This feels like it's about managing the computational constraints of the LLM in real time.
It's the cognitive scratchpad. We can define two types based on scope: managing a massive single input or managing a continuous dialogue.
Let's start with single-turn working memory, which is for input condensation.
This is for when you're processing massive, immediate inputs, a long document, dense logs, a high-dimensional video stream, all within a single forward pass.
The context window bottleneck is always the enemy here. How does working memory handle it?
Through condensation techniques. You have hard condensation, which discretely selects tokens based on importance. LM Lingua, for example, just discards predictable or repetitive content. It gets high compression, but you risk severing semantic dependencies.
And the opposite approach is soft condensation.
Soft condensation encodes variable length contexts into dense latent vectors. It turns dozens of input tokens into just one or two dense vector representations. It achieves very high compression ratios, but it requires additional training, and the information is no longer human readable.
Beyond just compressing text, there's observation abstraction.
Right, this is critical for agents in complex environments. Instead of processing every line of raw HTML or every video frame, systems extract semantic state descriptions. It maps a high-dimensional space into a concise summary that's easy for the LLM to parse, drastically cutting down on tokens.
And finally, we have multi-turn working memory for temporal state maintenance and continuous interactions.
In long, continuous interactions, the bottleneck isn't just the size of one input, it's the continuous accumulation of history. Working memory has to act as an externalized state carrier.
How does it do that?
Through state consolidation. It maps an ever-growing trajectory into a fixed-size state space through recurrent updates. Systems like MemAgent or Resum will periodically distill the entire interaction history into a single optimized reasoning state. This summary is then used to condition the next response.
So the agent can look toward the future without drowning in its own past.
That's the goal. Working memory ensures the agent remains focused and efficient, regardless of the complexity or length of the task.
Okay, this is truly the engine room of agency. We're now looking at the technical processes that transform raw data into actionable memory. The how.
Yes, the specific mechanisms behind those three conceptual operators: formation, evolution, and retrieval.
How does the system intelligently decide what's worth keeping and how to structure it? Let's start with memory formation.
The first major method is semantic summarization. This is inherently lossy compression. The goal is to distill the gist from lengthy logs, prioritizing the overall meaning over local factual precision.
And there are two main ways to do this.
Two primary paths. First, Incremental summarization, where the system fuses new information with the existing summary, chunk by chunk. Early systems like MenGPT just use the LLM's general summarization ability, but this often leads to topic drift.
How do modern systems fix that?
Systems like Mem1 introduce external evaluators or even use reinforcement learning to check the new summary against the old history for fidelity, actively avoiding that conceptual drift.
And the second path is partition summarization.
Partition summarization uses structural decomposition. Instead of one continuous summary, it divides information into distinct semantic blocks. Say, all interactions about task A get summarized separately from task B.
What's the advantage of that separation?
Superior efficiency and organization. The agent only needs to retrieve the summary for the relevant partition. The trade-off, however, is you risk losing cross-partition dependencies.
Next up is knowledge distillation. This sounds much more targeted than summarization.
It is. Distillation extracts function-specific knowledge core facts, user intents, or procedural strategies. Instead of a narrative summary, you pull out core insights and rules. It's not about describing what happened, it's about extracting the why and the how for the future.
And finally, a structural method. Structured construction. This turns amorphous data into organized graphs or trees.
This is a powerful formation operation because it embeds complex logic directly into the memory structure. You can do it at the entity level, decomposing text into atomic entities and their relations, like subject-predicate-object triplets.
Or at the chunk level.
Exactly. Chunk-level construction treats continuous text spans as nodes and organizes them. Raptor is a sophisticated example. It recursively clusters and summarizes related text chunks, iteratively forming a hierarchical tree structure.
The main advantage of all this structured construction is explainability and precision.
It is. But the downside remains schema rigidity and high maintenance costs.
Okay, so once formed, memory must be maintained. The evolution stage is all about ensuring consistency and relevance over long periods.
The first step is consolidation. This is about transforming those newly acquired short-term traces into structured, generalizable long-term knowledge. It reorganizes fragmented information, synthesizes high-level insights. This is where raw observations become wisdom.
Next is updating, which is where we hit that famous stability-plasticity dilemma again. When do you overwrite old knowledge versus treating new information as noise?
Updating ensures accuracy. For external memory, like in a vector database, the field has evolved. Early systems use simple destructive replacement, just overwrite the old memory.
But that feels risky.
It is. Modern approaches favor temporally aware soft deletion. ZEP, for example, will mark conflicting facts with invalid timestamps rather than deleting them, which preserves the historical record. More advanced systems use a dual-phase update. A quick online update, followed by a slower, offline reflective consolidation phase.
And updates can also happen internally, via model editing.
This is for when the memory is parametric. Model editing modifies the model's internal parameters. Roam is a method that identifies the exact parameter region encoding a specific fact and performs surgical weight updates only in that local region.
Finally, we need forgetting. The process of pruning obsolete data to maintain compactness. If you never forget, you just drown in data.
We see three classic mechanisms. Time-based decay, which prioritizes recency. Frequency-based pruning, like LRU algorithms, which removes things that are rarely accessed. The risk there is you eliminate valuable, long-tail knowledge.
Which brings us to the most sophisticated method, importance-driven forgetting.
This integrates multiple signals, temporal, frequency, and semantic. Modern systems leverage the LLM itself to assess memory importance and perform conscious forgetting. The agent is actively deciding what to retain for its own benefit.
Now we come to retrieval. This isn't just a database query, it's a dynamic cognitive process with 4 distinct steps. Let's start with retrieval timing and intent. How does the agent decide when it needs to access memory?
The field has moved from passive, human-driven triggers to autonomous, self-regulated decisions. The simpler approach is explicit invocation, where the LLM decides if retrieval is necessary based on the ambiguity of the current situation.
But the more advanced approach uses a concept from cognitive science. Fast, slow thinking.
Exactly. Systems like Comarag implement this dual process. They first generate a fast, low-effort response using only working memory. If the agent evaluates that response as inadequate, it autonomously triggers a deeper retrieval and reasoning phase.
So it only incurs the cost of deep retrieval when it's truly necessary.
Precisely. Now, Once the agent decides it needs memory, the next challenge is query construction, bridging the semantic gap between the current input and the memory index.
Raw input queries can be pretty vague.
They can. So agentic systems use sophisticated planning. Query decomposition breaks a complex query into simpler subqueries, and query rewriting refines the semantics of the query itself to better match the index.
What's an example of rewriting?
A classic is HIDE, hypothetical document embedding. Instead of using the raw user query, the LLM generates a high-fidelity, comprehensive hypothetical document that represents the ideal answer. The embedding of that document is then used for retrieval, and it leads to vastly more relevant results.
Okay, so once the refined query is ready, the agent applies its retrieval strategies.
This is how the agent searches. You have lexical retrieval, which is keyword matching. It's fast and precise, but struggles with synonyms. Then you have semantic retrieval, using embeddings, which is great for capturing context, but can sometimes be a bit fuzzy.
And the most robust method combines them.
That's hybrid retrieval. It integrates lexical and semantic methods, sometimes with graph topology expansion, to balance precision and contextual understanding. It gives you the best of all worlds.
Finally, we have post-retrieval processing, which refines the noisy, fragmented results into a concise, accurate context for the LLM.
This is the filtering and synthesis stage. It involves re-ranking and filtering using an LLM-based evaluator to estimate the relevance of each retrieved fragment and remove irrelevant or outdated memories.
And the final step is aggregation and compression.
This merges those fragmented, re-ranked memory items into a higher-level distilled knowledge representation that's compact enough to fit into the context window. It ensures the final memory context is aligned not just with the query, but with the agent's specific task requirements.
This has been a deeply technical breakdown. As we look forward, what are the primary challenges and research frontiers in agent memory, starting with the rapidly expanding field of multimodal systems?
The challenge in multimodal memory is immense. It's about integrating diverse sensory inputs, images, video, text across long time spans without fragmentation. The old methods, like simple frame sampling for video, were very brittle.
So the paradigm is shifting from these finite context windows to more continuous structured state representations. What are the current architectural paths to solve this?
We're seeing three promising paths emerge. First, state-space models, like Mamba. These compress infinite history into a fixed recursive state, offering a kind of theoretically infinite memory capacity with constant inference costs.
What's the second path?
Explicit memory banks. These maintain external storage of historical representations for precise recall. And third, sparse memory and retrieval. This balances efficiency with long-term adherence by augmenting current observations with sparsely sampled historical frames.
Beyond the architecture, what are the key challenges around trust and security?
Privacy is paramount, especially as these agents interact with sensitive user data. Future systems have to support granular permissioned memory, allowing the user to dictate what the agent can and cannot retain.
And for building trust, explainability needs to improve.
Absolutely. Explainability requires traceable access paths, the ability to look back and see exactly which memory fragments influenced a decision. We're moving toward tools that can do counterfactual reasoning, asking, what would the decision have been without this specific memory?
Finally, memory management directly affects the perennial AI problem of hallucination mitigation.
Yes, a robust memory system is the best defense against fabrication. Strategies include robust conflict detection, multi-agent cross-checking, and crucially, teaching the agent uncertainty-aware generation, teaching it to abstain or admit ignorance when it has low confidence in its retrieved memories.
This brings us to a fascinating, almost philosophical question. How does agent memory fundamentally differ from our own, and what does that imply for the future of AI?
The divergence lies in the dynamic of fidelity. The vast majority of existing agent memory systems rely on verbatim retrieval. They treat memory as an immutable repository of high-fidelity veridical tokens. Agents, by design, possess a perfect historical record.
They have a perfect recall, which is a trait humans famously lack.
Precisely. Human memory is inherently a constructive process. When we recall an event, the brain actively reconstructs it based on our current cognitive state, our biases, our emotions. We don't replay exact recordings, we build an abstract.
So the agent's memory is better in terms of factual accuracy, but perhaps poor in terms of abstractive flexibility.
That's the tension. Agents lack the biological capacity for this memory distortion and dynamic remodeling of history that characterizes human intelligence. They struggle with the creative, sometimes inaccurate generalization that allows us to apply an old memory to a radically new situation. And that fundamental divergence is where the future research frontier lies.
What stands out to me here is the sheer sophistication of the modern agent stack. It's so clear that simply having a lot of information isn't enough.
No, agency requires a comprehensive cyclical system that actively decides what to keep, when to abstract it, and how to find it precisely when needed. We've seen the architectural split token, parametric, latent, and the functional split, factual, experiential, working, and it proves that an agent's memory is far more complex than just a bigger text box.
Absolutely. And if we connect this to the bigger picture for you, the listener, understanding these three forms and that formation, evolution, retrieval cycle is the key to evaluating the true capabilities of any LO agent.
Right. An agent with strong parametric memory will excel at role-playing, while one with robust token-level memory will be auditable and transparent. The choice of memory is the choice of competence.
Which raises an important question then. If current LM agents are defined by this reliance on verbatim retrieval, and therefore they lack the human capacity for memory distortion or constructive abstraction, what entirely new capabilities might emerge when AI memory systems learn to dynamically remodel and reconstruct their own history?
What happens when they move past the static record and toward a truly constructive, generalized memory system?
Something to mull over until our next deep dive. Thanks for joining us.